welcome everyone again at the Craft Like a Bosch online hackathon. I think that we just reached the most exciting part of the hackathon, since now we will get the chance to get to know the finalists and also the best ideas during the weekend. You may know that we had 3 challenges in the topics of software development, hardware development and innovation, and we have 6 teams here with us who have been chosen as the best ideas in the hackathon. So in the previous hours, the jury members could evaluate the projects for each challenge, and they had the chance to select one challenge winner for each challenge. And while they were evaluating, the teams could also vote for each other in the Junction app, which uses a specific algorithm named Gavel. And this is how we got also 3 challenge winners as rather community winners who got the highest points from the teams. So now we have 6 teams here, but before they would start their pitches, I would like to introduce you the evaluation process for the grand voting and the audience award voting. And yes, let's see how they will be chosen. So for the grand winner, the teams will have to go to the Junction app after the last pitch, and they will see the finalists on the left side of the Junction app. They will see 6 teams there, 6 teams name, and they will have to choose one team, their favorite project, to be the grand winner. And while the teams are choosing, the partners, I mean Bosch and its mentors, jury and experts, can also vote for their favorite project, but they will get a type form or a Google form with the 6 names of the finalist teams, and they will also have to choose one team from these 6. And this is how we will get the grand winner, and we will have another kind of voting, the audience award winner, and this will run in the Hackathon's official Facebook event. So we will share the events link in the Hopin chat, you will see that, and there you will be able to choose also one project. But here we not only have the 6 finalist team, but all of the projects that have been submitted to the hackathon. So I think that there will be around like 15 projects. That was the final number for the projects submitted, and you also have to choose one project, and this is how we will get an audience award winner too. We will announce the grand winner and the audience award winner at the closing ceremony at 5 p.m. So stay tuned. Don't leave the Hopin after the last pitch, but choose for your favorite, and let's see who will take home the most money. So now I think that we can start with the pitches, and I will have only one question, ask for you. That's please use the Hopin chat and ask questions from the teams, because after each pitch there will be a chance to ask one question from each team. So if you want to, I don't know, it's not, so if you want to ask anything from them, you will have the chance to use the Hopin chat. As I mentioned, we will have 6 teams here with us, and two teams from each challenge. One is the chosen one from the jury, and one is the chosen one from the community voting. So the first challenge will be the software development challenge, and we will see the first team who has been chosen by the jury as the winner of this challenge, and this is not other than Like a Bosch Hackathon Software Development Challenge. What a creative name. And they will do the first pitch, but before they would pitch, we will play their YouTube video. So I would like to ask my stream team to play the first YouTube video.
This is a short presentation of our solution for the Craft Like a Bosch Software Development Challenge. We have created a GUI in Pygame to demonstrate a simulation of a parking vehicle equipped with ultrasonic sensors. The GUI is separated into 2 major parts, the playing field and the control panel. With our drag and drop features, we can freely and interactively move the shapes on the playing field. We can also rotate the rectangles, and as can be seen, our simulation real-time draws out and calculates the ray tracing lines according to the cross-echoes and the direct echoes. The color of green represents a direct echo, and the purple represents the cross-echo. We can reset and start the animation anytime with the buttons on the control panel. If the car gets too close to an obstacle, the control algorithm immediately stops the car. The sensor values are represented down in the table. Thank you for your attention.
Okay, now we have the first team to do the pitch, and I would like to ask Danielle to switch on your camera because we cannot see you, only your name, and it would be great to see you not in person but virtually. So could you please turn on your camera? Hey, yeah, nice to see you. So you will have 4 minutes to do the pitch, and you will hear a gong sound 30 seconds before your time goes. So I think.
Can you hear me?
Excuse me?
Hello, can you hear me?
Yes, we can hear you perfectly.
Okay.
So you will have 4 minutes, and can you start now?
Yeah, I would like to share my screen, please.
Okay. While you are sharing your screen, I would like to ask the other teams to share your screen while your YouTube video is playing, so you can prepare in time for your pitch.
Can you see the presentation?
Yeah, great. Okay, the stage is yours.
Okay. Okay. So hey, I'm Daniel. So you've already seen the short presentation of the GUI. So maybe I could talk about the mathematical concepts behind our simulation. So we had to create a simulation for this ultrasonic parking system. The two types of obstacles were the rectangle and the circle. And the two types of echoes are the direct and the cross echo. So this results in 4 base scenarios. The direct echo to the rectangular object is quite straightforward. First in the simulation, we have to calculate the echo points to draw the ray tracing lines, so we can gather where we can where are the echo points. In the direct echo rectangle scenario, it's quite straightforward. You just have to take the normal vector of the sensor facing side of the rectangle and draw a line through the sensor point. And the two lines, the side of the rectangle and this normal vector will result in a linear equation system. By solving this system, you can arrive to this intersection point, and that will be your direct echo point. In the case of the circle, it's even more straightforward. You just have to connect the center of the circle and the sensor point. And where the line crosses the circle, that will be your direct echo point. In the case of cross echo, you could arrive at the cross echo point for a rectangle by mirroring the sensor points to the sensor facing side of the rectangle. Then by connecting the opposite, the mirror of the other sensor with the sensor, you will have an intersection point, and that intersection point will be your cross echo point. This can be proven by basic geometry. So this normal through the M intersection point will be a bisector of the S1, M, and S2 angles. Once again, you just have to solve the linear equation system created by these S1, S2, and the other S1 and S2 lines. In case of the circle, we have used the brute force algorithm to find the minimal distance, find the distance minima of the S1M and MS2 distances. This will be your intersection point, your direct cross-sector point, I'm sorry. So, but there is another exact way to do it also by ellipse approximation method, where you draw a circle, draw an ellipse with the focal points of S1 and S2, and you write the equations for that ellipse and the circle, and that leads to a fourth-degree equation system. That's quite hard to solve, so we stayed with our brute force algorithm. So after arriving at these echo points, you can actually draw the ray tracing lines in the GUI. Our software architecture consists of three main things: the simulation model that actually calculates the tracing lines, the positions of the shapes and the sensor values. Then it feeds it to the graphical interface that displays everything. And the control module controls our car and reads the sensor values, then creates an intervening signal. Once again, this is how our graphical interface looks like. This was created in Pygame. So you can just start, reset, and stop the animation anytime. And you can drag and drop your obstacles on the playing field. Then the car will stop according to our control algorithm. Thank you very much.
Thank you. So actually, I think that there was something wrong with your presentation because we couldn't see the rest of the slides. But yeah, I think that you can share your presentation if you want afterwards, so everyone can check what
you can see my presentation.
Yeah.
That's
I'm
great.
looking for the hope in chat if there is any question to you and regarding your solution, but not yet. Then I will ask a question. How many hours did you sleep?
I don't know, not much.
Not much, okay.
I didn't count.
Yeah, but you were doing great, so thanks for the presentation, and good luck for the main prize. And let's switch to the second team, which is not other than who was the first one in the community voting. So they get the highest points actually, not only in the software challenge, but in all of the 3 challenges. And this is not other than the Peter the Parker bot team. So let's see their YouTube videos, and meanwhile I would like to ask Gabor, who will do the pitch, to share your screen in the Zoom chat, so we will, Zoom room, so we will be able to switch you right away into the stream. So let's see the video.
Hi everyone, my name is Gabor and this is my solution for the software development challenge. Peter the Parker bot is an easy-to-use scalable simulator for ultrasound sensors in a 3D environment. The problem of the challenge was to come up with an efficient working simulation of the direct and cross echoes of cars' ultrasound sensors. The ultrasound signal is a continuous one, therefore a greedy or iterative algorithm couldn't have been a good enough one. So I worked on an analytical solution. Firstly, I used mostly paper and pencil to try to visualize the problem to myself. After a while, I had some ideas, so I started to implement the ideas in Unity and made some UI improvements also. The link is in the description, so feel free to try it out. I would love to hear your thoughts about it. If you start the WebGL interface, then you will have two choices. If you want, you can start the autopilot mode with pressing the enter button, when the car will start to go backwards, and stop if an obstacle is getting nearby. The controls are quite easy. You can navigate the camera with these buttons and use the right mouse button to rotate the camera. You can also move the obstacles with the left mouse button, and if you want to rotate them, just press the left shift button.
You can start if you want. The stage is
Okay.
yours.
Okay, thank you. Okay, hi everyone. I'm Gabor and I have created the Peter the Parker bot solution for the software development category. I will also start with the mathematical part, because if someone is interested, then why not? Yeah, so the main problem was to create, not just create, but simulate the direct and cross echo for all the sensors based on the obstacles on the map. And my approach was quite straightforward. I had two types of objects, cylinders and cubes, and for those I created a 2D solution to calculate these lines and intersections. So for the first, the cylinder or the circle, the direct echo is quite easy. It's very straightforward. It will bounce back from the surface of the circle. In the cross echo situation, it's also quite easy. I had to create the center of the two sensors, and from that I used the same algorithm which I used in the direct echo part, so it will bounce back from that point. And if we use that point, then the reflection will be perfectly lined. For the cubes, it was a bit harder. The direct echo, I created the direct echo in a way that I tried all the four edges of the square, and I tried to put a perpendicular vector or line from the sensor to that edge line, and if the intersection was in the bounds of this square, then it's okay. If not, then it's not okay, of course. Yeah, and the hardest part was the cross echo for the squares. For this, I used several trigonometrical equations and standard, I don't know, mathematical theorems. I used the intercept theorem, the law of cosines, and the double angle identities. And from that, this magic has happened. I tried to search for any kind of paper or something on this problem, but I couldn't. So I was trying on paper to solve it in the night. So yeah, I had some typos, so it lasts a bit longer than it have should. But yeah, this started to work, and the framework was to do these four calculations for all the obstacle and sensor pairs, and also for the two neighbor sensors. And after that, I had to check if the angle is okay. So is it between the correct part, and if the distance is okay for the reflection. I use Unity to create this solution, and of course math. And yeah, you saw my video, so these snippets are can be like familiar to you, but I can do some live demo time, and yeah, you can try it out anytime if you want. It's on this itch.io web page. So yeah, basically you can use these obstacles to create some problem for the car, and hopefully it will stop in the right position. Also in the UI there is a on the upper left corner you can see what kind of data is getting into the sensors. So yeah, you will in a car you would see this interface, and if it's too close then you would stop.
Okay.
So yeah, basically that's it. Yeah,
Your time is up. I'm sorry.
Yeah. Thanks.
Yeah, it seems to be like my worst nightmare. I had a flashback into high school when I had these horrible math lessons and homework. So good for you that you understand them. And we have a question: what is the harder for you, this incredible GUI or the algorithm coding part?
That's a really good question. I used Unity several times, but I don't use it very frequently. So I always have to relearn those things that I already know, because it just disappears from my mind. So yeah, I think the hardest part was to come up with the cross-echo equation for the squares. But after that, I spent many time for the UI. Yeah, I tried to do a steering mechanism, so the player could steer the car, but yeah, that was 2 hours for nothing, because at the end I couldn't do it. Yeah. And 0 hours of sleep.
Yeah, but you had some Red Bull or energy drink.
No, I
Nothing.
don't drink coffee.
You don't
Just
need anything.
a small of like a tea, black tea.
Oh, nice.
That's all.
Nice. Okay, thank you and good luck. And let's see the third team. So we had the 2 challenge winners in the software development challenge, and now we move on to the hardware development challenge, where we also will have a winner chosen by the jury and a winner chosen by the community. So the first one will be the winner who was chosen by the jury. And okay, let's see the video first of all, and then the pitch of the team Discover team, who says that parking made easy with their solution. Yeah.
Anyone who is driving regularly in the city knows how hard it can be to find an empty parking spot downtown. Actually, drivers in Hungary spend on average 30 hours per year looking for parking spaces. But what if we knew where the free spaces were? We are Team Discover, and we have prototyped a parking spot scanner which can be mounted to the side of a car, even the old ones, and be able to detect empty parking spaces on a street when we pass them by. By uploading these free parking spaces to a central database, the system can let other drivers know where available parking spots are. So let's see how it works in real life. We stick the scanner equipped with an ultrasonic sensor and camera to the side of the car and connect it to our phone via Bluetooth Low Energy. And just like that, we are ready to go. Let's roll. You can see a real test here on the streets, where we are scanning everything to our right. The spikes on the graph represent the small spaces between cars, but if the space is long enough, then it could be a parking spot. And as a second layer of information, we have a video feed as well, so that we can double check whether a free space is actually a parking spot or not. Once the data is uploaded, the system will be able to navigate other drivers using Waze to the available parking spaces. We have soldered together an ultrasonic range sensor, a camera, and a Bluetooth module, and put it all into a 3D printed housing. We also worked out the details of the hardware architecture and schematics. You can learn more about them in our technical documentation. We are Team Discover, and we make parking easy.
Is it okay like this? Thanks.
You can start.
Hi everyone, I hope my presentation will work. So, we are Team Discover and we make parking easy. So I'm sure many of you who drive regularly in the city know how hard it can be to find parking spots downtown. Actually, we found that on average, drivers spend 30 hours a year only looking for parking spaces. Now, this is not only just a bad experience, but it's also detrimental to the environment by higher CO2 emissions and also higher fuel consumption. So how can we change these numbers? So we've come up with a small device that we can attach to the side of a car and is able to detect free parking spaces when we pass by them cruising in the city. So this works with an ultrasonic sensor and a camera, and we can monitor the parking spaces constantly when we are just driving on any streets, and then upload the data and let other drivers know where these available parking spaces are. And we actually went out and tested the prototype that we did in under a day. So yesterday we attached it to our car and went out on the streets of Budapest to see how it works. And to our pleasant surprise, it worked quite splendidly. So what you see here on the graph is the actual measurements we did with the ultrasonic sensor. So when you see the spikes and the short green flags, those are the spaces in between the two cars, and the longer green spaces or the longer parking spots that could be suitable for parking. And we also have a camera system complementing this so that we can double check whether these spaces are actually a parking spot or not, whether they are a disabled parking spot or just a garage entry. So it's another layer of information. We imagine the architecture that the processing will happen locally as a system on chip, and we send the output to a phone connected via Bluetooth Low Energy, and it will be the phone with 4G connectivity that uploads the data to a cloud, and then that data will be available to distribute to the other drivers so they know
Or not. Once the data is up,
so they know where they can find available parking spots. So as I said, we did this in the last day with 3D printing. So you see here one of our first prototypes. We actually experimented with several designs. Here you can see also an evolution of the current model. So the first two versions were printed with FDM technology. It's a simpler technology. And then the third one is actually with the resin-based 3D printing, which yields a smoother first surface, and it's also more aesthetically pleasing. We also worked out all the hardware architecture and schematics of the electronics together with a bill of materials as well. And we also had all the considerations in mind relating to weather conditions, so whether how it would work in harsher conditions during the winter or in higher temperatures during the summer. Also thought of electrical and mechanical stress considerations, and also did power and energy consumption calculations. And you can find more about these in our technical documentation that actually became quite, or have gotten quite long in the end, but you can find it on our junction submission. So we hope that with this small system, we will be able to make existing and older cars smarter as well, and create a better parking experience for the entire driving community. We are Team Discover, and we make parking easy. And we are happy to receive any of your questions. Well, I didn't show this, but here it is in front of me, the actual device.
I'm amazed. Yeah, Yeah, great job. And we have a question right away. Can you detect if the sensor was corrupted? For example, the weather is foggy, or there is an obstacle in front of the camera, or just the camera will be dirty during the drive?
Yeah, so actually the first time we went out and tried it, it was, I think the first night at 2 a.m. So it was quite cold. And we actually experienced that the sensor was having a hard time coping with the cold. So we had to heat it up a little bit to get it working again. So if it's definitely something that there is a real risk if we could, if we are thinking about the final product. But so far for the prototype, we couldn't really do that much about it. But yeah, the weather conditions are actually one of the riskiest factors that we need to take into account.
Great. And there is another question, which I have too. How did you design this? And you done a code and the video in less than 2 days. So Jakob's question is that what is your secret formula to to do a project like this in less than 48 hours?
Well, this is not our first hackathon. And actually, we really like hardware development. So we have 5 3D printers in our office. So we are used to designing and doing rapid prototyping with such ideas. So that's why we could do everything in parallel. There were 4 of us. And so we did the 3D printing. We also have an expert in film, how to say it, video editing, and we also have an embedded engineer who did the coding for the sensor. So it was all happening simultaneously.
Great. Okay, there are other questions in the chat, but I think that you can answer them there if you want. And let's move on to the next speech, but congrats, you really done a great job.
Thank you. Bye.
So the 4th team solved the same challenge, the hardware challenge, and they got the highest votes in the community voting. And the team is not other than the Animal Collision Avoidance System, ACAS, or something like that. So let's see their YouTube video, and meanwhile I would like to ask the pitcher to prepare and share its screen. And after the video we will turn him or her in the stream.
Hi, we are a group of students from the Budapest University of Technology. Yearly, more than 15,000 large animals are hit on the roads in Hungary, which kills many of them and also threatens the life of the drivers and destroys cars. Here we provide a concept for solving this problem with an infrared camera system. The 2 infrared cameras are placed in the 2 upper corners of the windshield. They literally see in the dark. They detect wild animals 150 meters before the car reaching it. This would not be possible with the classic camera currently used. The high-speed MOST cables transfer the data in the system. The ECU collects the information from the cameras, and the vehicle dynamics calculates the position of the animal and determines the probability of the crash with high-end AI solutions. Here you can see a simulation of the system. When the animal is detected, the driver is alerted with visual and sound signals. Here you can see a flowchart overview of the whole system. It's divided into 3 integral parts: thinking, sensing, and acting, according to the sensor-actor paradigm of Bosch. The artificial intelligence algorithm processes the image and determines the possibility of collision. If it's high, the system slows down the car, and in the most severe case, it performs an emergency braking. The driver is also alerted by sound and light signals.
Can we start?
Yes.
So, hi, yeah, actually, as it was in the video, we are a team from the Budapest University of Technology. And we want to present to you the Animal Collision Avoidance System, which we named ACAS. And for the introduction, I would want to say that this is actually a true problem. It's a worldwide problem because just in Hungary, 15,000 roadkills happen in every year. And you can imagine over the whole globe, there are a lot more. And with our system, we could reduce this number by quite a large margin. You could ask, like, how big of a deal is when you hit an animal? Well, by a bigger bodied animal, it can cause serious damage to the car, but the passengers itself as well.
Some words about the technical part of the system. So the key components of the hardware are the infrared cameras, which can detect the animals even if they stand in the dark forest behind trees by 150 meters before the car reaching it. The system is also supported by the multi-purpose camera system developed by Bosch. The sensors have a very high resolution so that the AI algorithms can detect the animals in time. The communication between the parts of the system happen via MOST buses, which can transfer the high bandwidth images, and the smaller data amounts are transferred via CAN buses. The ECU, the brain of the whole system, does some noise filtering and then processes the images, and with AI algorithms calculates the probability of the collision and positions the animal in its own coordinate system so that it can determine when the collision is going to happen. Here you can see an overview of the whole hardware, from the energy supply system with electromagnetic compatibility filters, through the sensing actors, the cameras, the thinking part, the ECU, and the acting, so the actors like alerting the driver, or the infotainment system of the car, which can stream the video captured by the infrared cameras.
We also developed the way in which our ECU would base their decision on. So just a quick go through. If both cameras see the animal, that means it is in the danger zone. So we have to act. And that means we calculate the possibility of a collision. And if there is a high chance that we are going to hit an animal, then we want to be slowing down to a safer speed, at which the Bosch multipurpose middle camera can spot the animal if it will jump in front of the car, and activate the emergency braking system. We would also alert the driver as well.
Yeah, so why this is an innovation? This is a unique solution which doesn't exist yet. There are some animal alerting systems on the market, but they don't work really well. So the chance of collision is really high, but with our non-existing technological solution, we could drastically reduce the amounts of collision and road kills on the roads.
And we just want to thank you for your attention, and thank you for the other teams for voting on us. And we want to present to you our team, because it's a team of 5. Please come here from Budapest University.
Yay! It's really nice to see the whole team, even though we couldn't be in the same area. And let's see, we have a question, or I'm not sure, but okay, let's do this. So, what is your sensor's energy consumption, and they can run in real time?
We couldn't really do real good estimations under this time, given that we don't have these cameras, don't have the ECU in itself. So, I mean, we would guess that the ECUs and cameras would consume the average power. I mean, the ECU, we would think it's kind of like in 1 watt power. So I wouldn't think, I mean, it can run live. Definitely think that.
And another question. So did you do a price estimation of the hardware based on the BOM, especially that 2 NIR? I'm sorry, I don't even know what these are means.
Yes,
but
we
so
have
especially
also
that's 2
price
NIR
estimations.
Yeah.
Sorry?
That's it.
Yeah, so we have also done price estimations. Yes, the most expensive parts are the infrared cameras, but we think that approximately from 80,000 forints, you could build up the whole system. And if a big multi-company like Bosch starts developing such a system, the cost can be reduced drastically because of the high amount of systems produced.
And the mass production.
Okay. Great. Good luck, guys. Actually, one of my biggest fear is that I would hit an animal while I'm driving. So I hope that you will get somewhere with this idea. But let's see the next team. So we had 4 teams from the hardware and the software challenges. And now we move on to the innovation challenge, which you may know that the teams have to come up with an idea that can help the Budapest parking situation. So the jury chose the Parkingverse team as the challenge winner of this challenge. So let's see their YouTube video, and then after that they will do also a 4 minutes live pitch. So yes, I would like to ask for the video. Thanks.
Do you know how hard it is to find a parking spot in central Budapest? Because we know exactly. During the past 48 hours, we developed Parkingverse, a fully functional simulation environment that is able to evaluate smart parking systems. This means that even though we can't tell what kind of smart sensors will track the streets in the future, we already have the solution to test these. Currently, we are validating a concept where 35% of the cars are equipped with smart sensors and they can share parking spaces with each other. Together with regular cars, they are displayed with colorful emojis on the map. Parking spaces are represented with circles according to their state in the real world and the one currently shared by smart cars. Smart cars will always navigate to the closest empty parking space to their destination. As they reach the final spot, they update the status of the parking space for other smart cars to know. In the meanwhile, regular cars have to go around randomly until they find an empty space. When regular cars arrive and leave from parking spots, smart cars won't know about these changes immediately, so we highlight this difference between the real world and the shared one. You can also see how smart cars are correcting this wrong information immediately as they drive by. During the simulation, Parkingverse records the time that each car spends on looking for a parking spot and also the distance between the found space and their actual destination. In our case, the simulation showed that smart cars found the parking spot more than 3 times faster and also closer to the destination compared to regular cars. Of course, in Parkingverse, we could easily repeat this simulation with different parameters and even take into account future scenarios like autonomous vehicles sharing their route with each other. This is Parkingverse, and we make sure that smart parking systems are actually smart.
You are on screen, Marcy. You can
Wanda.
start your pitch.
Perfect. I'm going to share my screen now.
No, not yet. But now. Okay, you can start.
All right. Hello, everyone. We are Team Parkingverse, and we are testing smart parking systems for their smartness. So I guess the problem is pretty obvious for everyone as of now. Finding an empty parking spot in a crowded city is a huge pain. To solve this, cities and manufacturers are coming up with different solutions, and they are called smart parking systems. Their job is to sense the empty parking spaces in the cities, track this information, and then distribute them to other cars, for example, through Waze or other onboard systems, as you could see, for example, in the Team Discover's pitch before me. Now, the problem is that we can't exactly know that these systems actually work because we have no way to test them. And this is why we created Parkingverse. Parkingverse take a smart parking system like this and puts into a virtual simulation environment. It creates different cars with destinations, and they are going through the city on their routes. While in the end, they will try to find an empty parking spot. Parkingverse visualize this whole process, then collects the data and analyzes in the end. This way, we can benchmark the smart parking systems. The challenge presented by Bosch was actually the perfect way to test how our system works, because in this case, they gave a scenario where 35% of the cars in the 5th district of Budapest are equipped with a smart sensor that is able to share the status of parking spaces with other smart cars. And this is how it looks like on our solution. This is the 5th district of Budapest. And you can see that how the thousands of cars are going around. They are the yellow and the blue markers. And also you can see the parking spots with red and green spots if they are empty or occupied. Now, this is actually a working application. So it runs on my computer, and what you see is a live recording. It has a backend that runs on Python and simulates the whole process, and the front end that visualizes the current state. If you take a closer look, you can see that the parking spots have different status based on their status in the real world and their status what the smart cars know about them. This might differ in some cases. And also you can see that the blue emojis represent the regular cars without sensors, and the yellow ones represent the smart vehicles. You can also see a white circle around them if they are starting to look a parking space when they arrive to the destination. This is how it looks like, and you can see that when you take a closer look into the map, you can see an example of the different scenarios that I presented before. And when we look at the video, for example, here, you will see that as a smart car arrives to its destination, it will park into its space and it will turn to red. Next up, you will see when the car leaves from a space, right here, this will turn to a space that is actually free in the real world, but occupied in the simulation world, and then the smart car comes around and will correct this information. After we run the simulation, we actually have quantitative data that the smart cars are finding an empty spot 3 times faster and also much closer to the distance compared to regular cars. So we can see that the system presented by Bosch is actually a good one. This is Parkingverse, and we believe that this is the future how we test smart parking systems.
Thanks. I would be really grateful to have a system like this, because when I just came to the studio, I spent like, I don't know, 15 minutes to find the free parking slots. So please, guys, do this, okay?
I'm always up for business, so we can talk.
Okay, so, but we have a question here. How did you send the data to the other cars, and how did you store the parking space and time?
So currently, this whole simulation runs in Python, and there is like a shared database between them. Because this is a simulation, we don't actually, so it's not part of the challenge to actually sense the empty spaces. This was like, for example, in the hardware challenge, as you could see before, it was given that there are incoming signals about empty and occupied parking spaces, and also that we can share this information back to the cars. So it's actually the role of a smart parking system and just simulate these signals to the cars.
Thanks. Any other question from David? Did you get your answer? I'm just talking to the Hopin chat right now. How many cars did you include into the simulation? I'm sorry.
So we currently simulated 8,000 parking spots in the 8th district. And also we simulated around 7,000 cars. So it was pretty crowded to find a parking space.
Wow. Great. Okay, thank you. And I wish you two good luck. And let's see the last team who also solved this challenge, but let's see how they solve this. So we will play the YouTube video of the Community Parking System Implementation and Simulation CPSIS team, and then they will also do a live pitch in 4 minutes.
Good morning, Bosch team, judges, organizers, competitors, and audience. My name is Lucas do Prado Pissolati, and today I will show you the most innovative application solutions for parking in the heart of the city center of Budapest, in District 5th. The power of parking is in your hands. Our hybrid application mobile for Android and iOS systems, SPSIS, provides parking smart solutions anywhere, anytime. Easy, innovative, economical, and environmentally friendly is what makes our company move forward to a better world in which technology comes to help and provide. Therefore, users save lots of money and time when finding the best spot to park according to their preferences, less traffic jam, and successful parking attempts. Optimization of used space for parking according to the vehicle size, significant amount of toxic emission pollutants such as CO2 are reduced, psychological problems such as stress related to finding free parking spots and executing maneuvers in challenging spots while parking are gone. And our future plans are to integrate the app with autonomous vehicles infotainment platforms to make your life even better. So now let's check our product in real life. Thank you very much for your attention and have a nice day.
Hey Lucas, you are on
Hello.
screen. You can start your pitch if you want.
Good afternoon. I would like to share my presentation with you. Okay, can I start?
So you shared your screen? Yeah, that's great. Now
Can you
it's
see
your
it?
time. Okay.
Okay. Good afternoon, ladies and gentlemen. First of all, I would like to thank you for all your support, which made it available for my team to win the Challenge Winners by Community Award and be part of the finalists in this program. As you can see here, we have a map of the 5th district. And I would like to start this speech by showing you a practical real-time simulation through the 5th district of Budapest. So I'm Lucas do Prado Pissolati, one of the creators of the innovative CPSIS app, which provides the smart solution for parking community systems anywhere, anytime. So as you can see here, we have a real-time simulation through the Sumo app, and it provides us real-time traffic and other concerns. And as you can see, sometimes there can be some traffic jams regarding either accidents, traffic lights, or parking attempts. And nowadays we face some problems related to economical, environmental, psychological, and timing concerns. Vehicles are, for instance, the majority responsible for 72% of the pollutant emissions resulting in the global warming in the world. And in 2018, in the state of São Paulo, 2,099,000 tons of CO2 and other thousands of tons of pollution were emitted to the environment. So imagine if we can drastically reduce the amount of pollutants and in the environment, not to mention how much fuel could be saved in avoiding time stuck in traffic and timing. Hungarians in average spend 30 hours per year trying to find a parking spot, and sometimes it's not even the best one. And during traffic jams, the average of drivers in general can take up to 30 minutes. Imagine how better you could spend this time right. Therefore, our app mobile provides localization, traceability, and to specific right locations. So basically, here's our app, and the user downloads the app. If he doesn't have an account yet, he comes to this register now. He enters his personal data, such as name, age, bank account, car model, and so on. So he makes the login, and it registers him into the system, and he can sign up and choose the best spot that he would like to park in. So we are in the area of Budapest, and let's say he wants to stop right here because it's the nearest one near his house, the Zechenyi utca. So basically, our app has a data based in MySQL, which connected to the PHP backend provides some information about this car and other issues as well. So it gets the size of the car, the weight, etc. And it traces through the APIs of the Google Maps our right real-time location, and from there where we want to reach. So it also estimates the time, the distance, and in case there is some traffic or some traffic jam or some accidents on the way, it also updates us. And when we reach this place, if he wants to book this place, he comes to this page and he makes the reservation. And when he reaches the place, he can park in. And to avoid some kind of problems that someone could park in his place, then we provide with the major of the 5th district or other districts the hardware implementation of sensors such as ultrasonic, some bars that go up and avoid other users to connect to this parking lot. And this is based on the front-end PHP, JavaScript, Python, CSS, and Cordova in Android and iOS devices applications. Our implementation would cost probably about 15,000 euros. And thank you very much for your attention. If you have any questions, I would be happy to answer you as much as I can.
Thank you. Thanks. Where did you come from? You live in Hungary, right? But
yes, I currently live in Hungary and I come from Brazil. I am currently doing my master's in autonomous vehicle control engineering at BME University, and this is my first hackathon.
Oh, nice. And since when do you live in Hungary?
I came last year in August 14th, yes.
Yeah. And do you drive often in Hungary or not at all?
Unfortunately, in Hungary, I don't drive at all, but I have friends who drive, and I use all the transport systems as well, which are quite efficient. And I've seen different things happening in the parking lots, in the streets, so we can get some idea of finding the best solution for these topics.
Yeah, great idea and great solutions. So I thought that you somehow became familiar with the situation, but yeah. Okay, I cannot see any questions in the chat yet, but I think if you just join the hop-in, maybe there will be some questions later. But thanks for your solution and the pitch, and yes, so. Now we reached the last pitch, and we will start the evaluation process for the grand winner and the audience award winner. So now we will have like 45 minutes to vote for the best idea in the hackathon. Now we will have two kind of voting processes. One of them is for the audience award winner, who can win up to, no, not up to, but win exactly 500 euros. So how does it work? You have to go to the hackathon's Facebook event, which we will share in the hop-in chat soon. You will find all of the projects that have been submitted to the hackathon, and you will have to choose one project. Since the poll we won't be able to close the poll at 4:45 we will just do a print screen and then delete the post. So that's how you will see who got the most points for the voting. And while you are voting for the Audience Award winner, we will also have the winner for the grand prize, which is 2,000 euros, not 4,000 euros, I'm sorry. And the teams will be able to vote through the Junction app. You will see the finalist part at the left side of the Junction app, and then you will see the 6 teams who did the pitch just right now. And then you will have to choose one team from the 6. And the mentors, experts, and juries will get a Google form, and they will have to indicate their favorite project through that form. And then we will summarize the votes from the teams and the jury, and that's how we will get the grand winner too for the event. So you will have now around 45 minutes to make your vote. You can also vote for the Audience Award winner, and the teams can also vote for the grand winner. And then we will be back at 5 p.m. to announce the actual winner of the hackathon. So have a great time. Don't go far. We will be back shortly. And see you in the hop-in stage at 5 p.m. Thank you.